this module, we will discuss sequential reactions. In many chemical processes, reactants are transformed into final products through a series of sequential steps. Let's consider an example of a sequential reaction mechanism where a product C is formed from reactant A through an intermediate substance B into consecutive irreversible unimolecular reactions. This reaction mechanism is represented by the following reaction scheme. In this sequential reaction, A first transforms into B in a unimolecular reaction with a rate constant K1. Then B reacts further to form C in the second unimolecular reaction with a rate constant K2. The formation of intermediates is a key aspect in sequential reactions. Intermediates are transient species that connect the initial reactants to the final products but are not present in the final reaction equation. For instance, in our example of the reaction mechanism, the intermediate B is formed and then consumed in the consecutive steps. However, when we consider the overall reaction, it is simply represented as A to C. For our example reaction scheme, we can derive the differential rate expressions for reactant A, intermediate B, and product C. For reactant A, the rate of decomposition is given by d concentration of A by dt equals negative of K1 times concentration of A. This equation reflects the first order decay of A in the initial step of the reaction. Intermediate B is formed from A and then transforms into C. The rate of change of its concentration is expressed by d concentration of B by dt equals K1 times concentration of A minus K2 times concentration of B. This expression accounts for the formation of B from A and its subsequent consumption to form C. Finally, the formation rate of product C is described as d concentration of C by dt equals K2 times concentration of B. This is consistent with the first order reaction of B into C. Let us now establish the initial conditions at time t equals 0. We assume that only the reactant A is present initially with a non-zero initial concentration that we denote as C0. The initial concentration of the intermediates and products, in this case B and C, is therefore 0. Furthermore, we take into account that the sum of the concentrations of A, B and C at any time t is constant and equal to the initial concentration of the reactant A. With the established initial conditions, we can derive the expressions for the concentrations of A, B, and C over time for our sequential reaction. For the reactant A, the concentration at any time t is given by the integrated rate law of the first order. This equation reflects the exponential decay of concentration of A with time, governed by the rate constant K1. For the intermediate B, the concentration at time t can be determined by solving the differential equation with the initial condition that B is initially absent. The resulting expression is shown here. This equation captures the dynamics of B's formation and subsequent decay influenced by both rate constants K1 and K2. Finally, the concentration of the product C at any time can be derived from the mass balance and the concentration expressions for A and B. This equation reflects the cumulative effect of the sequential reactions leading to the formation of C and incorporates the influence of both rate constants K1 and K2. These expressions collectively provide a comprehensive understanding of the concentration profiles of reactants, intermediates, and products in a sequential reaction. In sequential reactions, the concentration time curves of reactants, intermediates, and products are rather intuitive when represented in graphical form. Let's consider a few scenarios to understand how the rate constants K1 and K2 influence these curves. In figure A, we observe the case where K1 equals twice K2. Here, the rate constants for the formation and decay of the intermediate are comparable. The reactant A undergoes exponential decay, leading to the formation of B, which subsequently decays to form the product C. The concentration of B initially rises, reaches a maximum, and then falls to zero. The product's concentration increases from zero, approaching the initial concentration of A as all A is converted to C. For larger values of K1 to K2, as shown in figure B, the reactant A is rapidly consumed and the intermediate B is formed in higher concentrations due to its slower reaction rate. This results in a pronounced maximum in the concentration of B, which shifts to shorter times with higher values of K1 to K2. In this scenario, the rate of formation of B is significantly larger than its decay rate, leading to a greater maximum concentration of the intermediate as compared to the first case. Conversely, in figure C, where K1 is less than K2, the maximum concentration of the intermediate is significantly reduced. This is consistent with the situation where the intermediate tends to decay faster than it is formed, resulting in a smaller concentrations of the intermediate. In the opposing case, where K1 is higher than K2, as shown in figure B, the logic holds true with a higher intermediate concentration observed. To summarize, the temporal evolution of concentrations in sequential reaction is highly dependent on the relative magnitude of the rate constants K1 and K2. These dynamics are crucial in understanding the behavior of sequential reactions and predicting the concentration profiles of all species involved. A remarkable aspect of sequential reactions is the behavior of the intermediate species, particularly its concentration over time. It is described by this equation. As we observed in the concentration time curves, this concentration rises from zero, reaches a maximum, and then falls to zero. We have also noticed that the peak concentration of the intermediate is influenced by the rate constants of its formation and decay. This raises an important question. Can we accurately predict when the concentration of the intermediate will be at its maximum? To find this, we need to consider the rate of change of B over time. The maximum concentration of B is reached when its rate of change with respect to time is zero. Mathematically, this is represented by the derivative of B with respect to time being equal to zero at the time of maximum concentration, T max. By applying this condition to the previously derived expression for the concentration of B, we can set the derivative of the concentration of B with respect to time equal to 0 and solve for T max. The result of this calculation gives us the precise time at which the concentration of the intermediate is at its peak. Here we also would like to mention that the equation describing the concentration time curve for an intermediate in a sequential reaction is known as Bateman equation in some fields of science, such as pharmacokinetics. In pharmacokinetics, the Bateman equation is employed to model how a drug concentration changes in the body over time, considering both the absorption phase, where the drug concentration increases, and the elimination phase, where the concentration decreases. The significance of this equation in pharmacokinetics lies in its similarity to the concentration time profiles for intermediates in chemical reactions. Just as we have analyzed the peak concentration of an intermediate in a sequential reaction, the Bateman equations helps in predicting the peak concentration of a drug in the bloodstream, which is crucial for determining effective and safe dosages. In our discussion of sequential reactions, we previously established that the rate at which a product forms is significantly influenced by the rate constants of both the production and decay of the intermediate. Within this context, we can consider two distinct limiting scenarios. The first scenario occurs when the rate constant for the decay of the intermediate, K2, is substantially higher than the rate constant for its production, K1. This is typical for cases where the intermediate is highly active and does not accumulate significantly. Mathematically, we can employ this condition to significantly simplify the expression for the concentration of the product C. If K2 is much higher than K1, these two terms can be neglected, and we obtain the following expression. In this limit, the time-dependent behavior of the product concentration mirrors that of a first-order decay process of the reactant A. This means that under these conditions, any intermediate that forms is rapidly converted into the final product. Consequently, in this limit, the overall rate of product formation is primarily dictated by the rate of the reactant decay. In the opposing limiting case, where the rate constant for the production of the intermediate, K1, is significantly greater than the rate constant of its decay, K2, the dynamics of the reaction changes. In this case, the reactant rapidly converts to the stable intermediate. The mathematical expression for the concentration of the product C in this limit is shown by this equation. The time-dependent behavior of the product concentration is analogous to a first-order decay process, but this time it is of the intermediate B, not the initial reactant A. It means that the rate at which the product forms is governed by the slower decay rate of the intermediate. This analysis of sequential reactions reveals an important approximation of kinetics. This approximation can be formulated as follows. If one step in a sequential reaction is significantly slower than the others, it dictates the rate at which the product forms. This slowest step is thus identified as the rate determining or rate limiting step. Understanding this rule is important for predicting and controlling the kinetics of a reaction, as it allows for a focused analysis on the step that most significantly impacts the reaction's overall rate.